I want to talk a little bit about equilibrium. At this stage in our mechanics class, every object looks like a point object. It looks like a dot because we don't know how to deal with rotation yet. And if we gave an object some dimension, some volume, some physical shape, it could rotate, and we can't deal with that yet. So every time we picture an object, a box, a person, it doesn't matter, a car, a cart, it always looks like a dot, like a point object to us at this stage. In a few weeks, we'll learn how to deal with rotation, and our objects can have dimension. But right now, our definition of equilibrium is just that there's no acceleration. What does that mean? The net force is zero. So that's our definition of equilibrium right now. The net force is zero. There's no acceleration. In a few weeks, when our objects have dimension and can rotate, we're going to add to this. We're going to say that there can't be any rotational acceleration either. And the way we say that is the net torque has to be zero. Just like forces cause acceleration, torque cause angular acceleration. So we're going to add to this definition of equilibrium in a few weeks. But right now, our definition of equilibrium is the net force equals zero. To get a better understanding of equilibrium and the different types of equilibrium, let's think about potential energy. Here I have a ramp, and I can release a ball at some location on the ramp, and that ball will roll down, and it will roll back up to the other side to basically the same height it started from. And it'll turn around and go back in the opposite direction, and it'll roll back and forth along that ramp. If we graph the gravitational potential energy versus distance, we would get a curve that looks just like the ramp because it's proportional to the height. So when our object is out here at its starting point, it has a certain amount of gravitational potential energy. And that's also the total energy the object has because it's starting from rest. We could draw a line across here, and that would indicate the total energy. So as the object moves down toward the bottom of the hill, it moves faster and faster and faster, and it gains kinetic energy. So if this amount, when the object is here, if this is our gravitational potential energy, then this would be our kinetic energy. And when the object gets to the lowest point, it has the least gravitational potential energy, and it has the greatest kinetic energy. What if we want to start our object from a higher height? Instead of starting it from here, we'll start it from up here. Now its gravitational energy starts from up here. The total energy of our system now is going to be higher up. There's more energy in our system. The object will roll down the hill, get to the other point where it momentarily comes to rest, and it will roll back. So these points are called the turning points. It's where the velocity equals zero. The total energy is defined, and we know that at any location here, no matter where our object is, we know that there's a combination of gravitational energy and kinetic energy. They add up to be the total energy of our object. If we start our object higher up, it starts with more energy. There's more energy in the system. It's going to be moving faster when it gets to the bottom. This would be a graph of gravitational potential energy. It would depend on the height of our object as it moved back and forth. There's a region out here that's kind of interesting What happens if our object starts from this point and turns around when it gets over here? So our total energy is defined by that line. Well, if this total energy at some point is our gravitational potential plus our kinetic energy, what happens in this region of space over here? This would be our gravitational energy. If our object was out here, this would be our gravitational energy. And so our kinetic energy would have to be negative in order to make our total energy this red line we see. And we know kinetic energy can't be negative. So there's a limit. Our object is bound by the energy it has. It can't go out beyond the energy it has. This is called a classically forbidden region. So we would say the object can't go there. It's classically forbidden. It has to stay within the bounds of its allowed energy. One more thing we want to notice is that while this object is moving back and forth within the region that it's allowed to move, within its bound energy, its total energy, it's going to get pushed toward the bottom of the hill. Our object, if we release it up here, it feels a force pulling it toward the lowest point. And if it passes that lowest point and ends up on the other side, it feels a force pulling it back towards that lowest point. The forces are pushing the object toward the lowest energy spot. So where would this end up if we let it go back and forth and a little bit of this energy was dissipated by air resistance or friction? It would eventually end up right at the bottom, at the lowest point, where it has the lowest gravitational potential energy. So the force pushes it back in that direction toward the lowest energy. But it doesn't depend on how much energy the object has. If the object is up here or in the middle or down here, it doesn't depend on that. What it depends on is how steep that curve is, the slope of that curve. If the object is up here where this curve has a steep slope, it feels a big force. And if the object is down here where the curve has a small slope, it feels a much smaller force pushing it back toward that equilibrium position. It's the slope of this curve that's important to determine the force acting on our object. The shape doesn't have to be that curved shape either. If I have a ball on a ramp like this, an inclined plane, and I let go of it, it's going to roll downhill. And as it rolls downhill, it's going to lose gravitational potential energy. So I could draw gravitational potential energy versus position curve, and it would look like a straight line. So if my ball starts out up here, the total energy of my system is defined by its starting point. The region out here would be the classically forbidden region, and the object would feel a force toward lower gravitational potential energy. And the force would depend not on where the object was, whether it starts out here, or whether we released it from higher up, or whether we released it from lower down. The force depends not on where we released it, not on the height. It depends on the slope of the line. And here, the force would be the same everywhere because it's a straight line. And we can have other types of potential energy. In this example, we have a mass attached to a spring. If we pull the spring away from its equilibrium position in this direction, it will have a certain amount of potential energy, spring potential energy. If we let go of it from rest at that location, that would define the total energy of the system. The mass would move from this location to some location on the other side, defined by this turning point. and it would oscillate back and forth between those two locations. As the mass moved to lower spring potential energy, like let's say here, it would gain kinetic energy. And at the lowest point here, that's the equilibrium position of the spring, the object would have its greatest speed, its greatest kinetic energy, and its lowest spring potential energy. And if we started out at this location, then it couldn't be higher, right? That's our classically forbidden region, and this is our classically forbidden region on the other side. It's bound by the total energy it has, and it can't exceed that. And like gravitational potential energy, we can look at this curve and see that there's going to be a force exerted on our object, pushing it back toward the lowest potential energy. So if our object is out here, it's going to feel a force in this direction, back toward the position where it has the lowest potential energy. And what does that force depend on? The slope of this curve. As we pull the cart to a bigger and bigger distance, the slope of this curve increases and the force on our object increases. It's easy to show how the force relates to the slope of the potential energy curve. We're going to start with our definition for work done by a constant force. We can assume that our force is in the same direction as our displacement because we're only dealing with a one-dimensional problem. And when we defined work and potential energy, we know that work is negative delta U. And that U could be gravitational potential energy, could be spring potential energy, some kind of potential energy term. And what do we get? Negative du dx is our force. And that would be the force in the x direction. So this tells us that the slope, we could write this as du dx, or negative du dx, is our force in that direction, in the x direction. The force is in the opposite direction of the slope of the potential energy curve. That means it's always pointing back toward lower potential energy. If the slope is positive, the force is in the negative direction towards lower potential energy. If the slope is negative, it's in the positive direction toward lower potential energy. And if you've had a vector calculus class, you know this is the vector gradient operator del, which is the partial derivative with respect to x times a unit vector in the x direction, plus the partial derivative with respect to y times a unit vector in the y direction, plus the partial derivative with respect to z times a unit vector in the z direction. So the force is negative del u. We're not going to deal with 3 dimensions. We'll just deal with 1 dimension. And if you haven't seen this operator before, you'll see it in your vector calculus class. The last thing we need to talk about with equilibrium are different types of equilibrium. We know that the net force is 0. We've already talked about an example where we have a bowl and you release a ball and it rolls back and forth. If there's some friction and air resistance, where's the ball going to end up? Eventually the ball is going to be right there at the bottom of the bowl, at rest at the bottom of the bowl. Is it in equilibrium? Yes. And we call that stable equilibrium because if we displace it a little bit from the equilibrium position, if we push it a little bit to the right, where is the force on the ball? Back toward the equilibrium position. If we push it a little bit to the left, where's the force on the ball? Back toward the equilibrium position. It wants to be at that lowest potential energy location. It's back to the equilibrium position. We call that stable equilibrium. But what happens if we take that bowl and we turn it upside down? And we take our ball and we very carefully balance it at the top of the bowl. Is it in equilibrium? Well, if we get it just right, there is a point there where the sum of the forces will equal 0. There is an equilibrium position there. But that's pretty tricky. Why is it tricky? Because if our ball gets displaced a tiny bit to the right, what direction is the force acting on our ball? Away from the equilibrium position. If we displace the ball a tiny bit to the left, what direction is the force? Away from the equilibrium position. So this technically is an equilibrium position, but any tiny displacement in any direction and it's not in equilibrium anymore. The ball moves. We call that unstable equilibrium.